Alright, hello everyone. So today we're gonna study a new circuit element, which is the operational amplifier, op amp for short. Um, I'm so used to calling it op amp. Is even going to say it the first time. Anyways, so an op amp. The first question is okay. So what is an op amp? What is an op amp? What is this new circuit element I'm gonna study? Well, in general terms, it takes a voltage difference. Okay, well, a voltage you could say, because a voltage is actually a potential difference, and it gives you another output voltage. All right. So you might think so, and it is a valid way to think about it. Is that it behaves like uh, voltage controlled voltage source, right? Or let's say VCVS, sorry, VCVS for short. Okay, and you wouldn't be wrong, but at least that's not how most people, or I don't think that's how most people think about it. And I personally also don't think about it like that. I think, I believe, as far as my experience goes, most people like to think about it as okay. So it's a very it's a very versatile circuit element that's able to do a lot of some mathematical operations based on your input voltages. So it takes two input voltages. Okay, so takes two input voltages. Okay, and it gives you an output based on that. Okay, gives an output based on, okay, that. And this isn't, you might say this isn't much different from what I wrote, but remember what I said. This output is actually going to, and usually is like that. So this output is going to be the result of, wait, okay, so why did I switch to that color anyway? So let's use a different one. Sorry about that. So this output is actually, whoops, okay, today is really messy. Okay, this output is the result of some kind of mathematical operation done on these inputs. So what the op amp does is it does some mathematical operation. Okay, so some math operation. So I'll let op here, and I think you can already see this is exactly why or the op amp does have the name it does. The operational part comes from here. Okay, so it does some, using these two input voltages, does some mathematical operation, like suppose say addition or subtraction, maybe multiplication, division. And when I first studied about op amps, this is what I found, very interesting and fascinating, is they can even differentiate and integrate. Okay, they can even differentiate and integrate. Okay, so operations like those. So and well, based on that, the op amp is going to give you a voltage output. So that is how really most people like to think about it. Okay, it's a very versatile circuit element that can do a lot of things, and depending on how you set up the op amp circuit. Okay, so moving on, let's see. Okay, all right. So, and well, the natural question is, okay, so how does an op amp look? And well, I have a picture of this. I have a picture of this, and kind of looks like a mechanical spider. To be honest, if I didn't know about op amps and this thing appeared in my dreams, I would be running at full speed in the opposite direction. But anyways, this is how it looks. This is an op amp. You have 8 pins here. I'll label them. So these metallic parts on either side, those are called pins. Okay, you fit some you connect something on those. So this is pin 1, this is pin 2, this is pin 3, this is pin 4. Instead of going here, pin 5 is actually the one adjacent to, exactly opposite to pin 4. So this is actually pin 5, this is 6, this is 7, and this is 8. Okay, and um, before your imagination might wander, and um, it's definitely the big question here. What is inside? What is inside this black box like thing? Okay, and surprisingly, the word black box would be very accurate to describe how we are going to treat this for um, the rest of the series, because the inside is actually pretty complicated. It's a complex arrangement. You have some you have transistors, you have capacitors, resistors, etc. I think the total number of things here can be 50 or even above that. I'm not sure of this figure, but yeah, I think um, you know as far as I remember, so it can be 50 or above. So it's a very complicated arrangement. For our purposes, we are only gonna worry about, okay, so what inputs does the op amp take, and what output it gives. So basically, what it does instead of how it does it. Okay, so yeah, as I said, we're gonna treat it like a black box, pretty similar to how it really looks. Okay, so this is basically how an op amp looks, but obviously we cannot work with something like a figure like this. We're gonna revert to our circuit diagrams. Okay, we're gonna revert to our circuit diagrams, and well, first I'd like to explain what these pins really are. Okay, let's see. So the most important ones are actually um, your pin 2. Okay, your pin 2, which is your um, inverting. I need to write these in full form, so that obviously this is the first time we're doing these, so cannot slack off on this. So this is your inverting input. Okay, this is your inverting input. Okay, and why this is inverting, and the other one is 3, which is the non-inverting input. Why they are like that, I'm going to discuss just a bit later when I draw the circuit. Anyways, so this is the in um, okay, so this is that's the inverting input. 3 is called the non-inverting input. Whoops. um, 3 is called the non inverting, and well, this much is enough for this. So non-inverting input, right? So these two are two of the three important pins that we care about. The last one, okay, so those are the inputs, and obviously I think you can guess that the um, other important pin is actually the output. It's going to be output, and it's actually the 6. Okay, and oh wait, I should have mentioned this. This is kind of like a technical detail, but the op amp we're working with is well, it's the most used model. Okay, it's the most common model. It's called the IC741. It's called the IC741, and this is the most widely used and seen model. So that's why we're gonna deal with this. Okay, so that aside, so yeah, the output 6. Okay, this is the output terminal. Okay, pin 6, this is the output terminal, so this is the output. um, I'm gonna pause for a bit. Alright, so I'm back. So as I was saying, so 6 is your output, pin 6 is your output, and these three, 2, 3, and 6, your two input terminals or pins, and the one output terminal pin. These are the most important ones, and basically what we are going to work with for most of the series. But anyways, I should also mention what the others do. It wouldn't be fair if I don't. So let's see. Let's see, 1 and 5. Okay, so there we have pins 1 and 5. These are called um, the offset null. Okay, the offset null pins, or well, to put it more simply, the simpler name is the balance pins. Okay, the balance pins. um, well, if I wanted to describe their roles as simply as possible, they make sure that your output voltage is 0 when it's supposed to be. Okay, they make certain of that. All right, but well, okay, so that's done. Um, your pins 4 and 6, okay, sorry, 4 and 7, I'll do it in a different color. Let's see, what did I already use? I definitely need to use different color here. um I use yellow. Yeah, I'll use this is more trickier than I thought, and I really shouldn't be wasting my viewers' times with this. Sorry. Okay, so you have your pins 4, okay, and your pin 7, pin 4 and pin 7. Um, these are the power supplies. Okay, these are the power supply terminals. So 4 and 7, this one and this one. Okay, these are your power supply. Power supply. Power supply. Your seven is actually the positive one. Okay, pin 7 is actually the positive power supply, and pin 4 is actually the negative one. Okay, so that's done. And the most trivial one is actually pin 8. There's actually no connection here. Okay, no connection. So it's for us, this is the most I mean, sorry, the least relevant one. There's no connection on pin 8. All right, so that should be enough with describing what the rows of these pins. But we definitely should move on to the circuit diagram. So let's see. If I just wanted to draw a circuit diagram of the op amp, it's going to look something like this. So let me see. All right. Let me see if I have. Okay. So yeah, nothing missed out. Nothing missed out. That's good so far. So, um, and well, this is how you're. This is how we draw an op amp. Symbol for an op amp is triangle. Okay, triangle, like this. All right. So this is how this is the symbol for an op amp. You have your two input pins here. You have your two input pins here. All right. Um, let's see, you have your two power supplies here. Let's see, I'll try to do this. Actually, let me do this in a different color. Let's see. Okay, so you have your two power supplies here. Let's see, this is one battery, this is another this is another battery, and let's see here, you connect them. That didn't look that well, but that good. And this is your ground. Your ground is here. This is your actually, yeah, that becomes a bit confusing with the cells. I'll do this in different color. Let's see, let's use light blue for ground. So this is your ground. Should have used green probably, but anyways, this is your ground. So with that done, let's label the port. And I forgot the I guess you could say the most important one. This is your output. This is your output. All right. So as we saw, your input pins. Okay. So first thing, your output was 6. Your output pin was 6. Your input pins are 2 and 3. Your input pins are 2 and 3. Right. So 2 is the the inverting one, okay, or the negative input, and again I'll explain why a bit later. So and that is actually the one you draw on the top, okay. Surprisingly, a bit surprisingly, but the negative one or the inverting one is actually the one you draw on the top. 3 or the non-inverting one is what you draw on the bottom, okay. This is a convention, so you should follow it unless the diagram is drawn in a different way, these two flipped. Okay, so that done, 6 is your output, all right. 7 here. Oh, whoops, not that color. 7 is your power. 7 is your positive power supply. Okay, so I'll draw a small plus here. 4 is your negative power supply. I'll draw a minus here. Actually, you can clearly see why. One thing is these two cells actually have the same value. We'll call that V capital C capital C. So this cell and this cell have the same value of V capital C capital C. I think you can see why I mean how 7 is the positive supply and 4 is the negative supply. Okay, so because this is the ground, so this is, you have your zero potential here. So this node, which is basically this whole thing, all the way up to your pin 7, this is going to have what whoops, this is going to have voltage of or potential of, let's see, plus VCC, right? So because your cell just gave it some positive potential, but here, when you go from 0 to when you go from your ground to your pin 4, your this terminal, this power supply terminal, your cell is actually in the opposite direction, the opposite polarity. So the potential here, okay, or the voltage here is going to be negative VCC. It's going to be negative VCC. All right, and that's why this is the positive one and this is the negative one. Okay, I hope that that is clear. So with that done, let's see if I missed out anything. No, no. Uh, this is a very I'd say this is a very, intricate topic, so I really want to check whether I've missed out anything or not, but seems like I haven't. Okay, so the thing that I've been waiting for is, okay, so this is our um, complete complete op amp, okay, our op amp circuit. But as I said before, the important terminals, okay, or the important pins are actually your two input pins and the one output pin, and I think it makes sense why. As I said before, we only care about what the op amp does. Okay, so and basically that means what output it gives based on what input it's taking. So pins 1 and 5, which just balance something. Pins 4 and 7, which are just the supply, the power supply for the op amp. And by the way, this have the op amp having a power supply does imply that this is an active element. Okay, so the op amp, is actually an active element. This is actually quite an important detail. So this is an active element. But anyways, so the balance pins, the power supply pins, the supply for the op amp itself, and obviously the one that has no connection. These are not really that, these are not important when we try to analyze the input output relationship, so we can ignore all those. And the only part we need to care about is this. The only part we need to care about is this. Okay, so i'm going to um, I'm going to take this here. Okay, so I'm going to take this part, um, and I'm going to actually crack it open. Well, not fully, because as I said, the op amp, we're going to treat it mostly as a black box. But in general, well, if I wanted to draw well, at least at the input and output ends, if I wanted to draw the equivalent circuit, okay, not caring about the things that are in the middle, which do most of the work, it's going to be something like this. So obviously I'll draw my triangle silhouette, although it's not really important here. I'll draw my triangle silhouette. um, okay, so what you have here is, let's see, and my mouse is getting bent, so wait, fix that. Okay, so this color. Okay, all right, so no more delays. So you have your two input pins. Okay, your two input pins. All right, this is your pin, this is your pin 2, this is your pin 3. This is, I mean, I think from now on, I should stop mentioning 2 and 3, because most of the time we just refer to them as non-inverting and inverting, when we're working with them. So your non-inverting pin, your a non-inverting input, your inverting input, but between them you actually have a resistor. Okay, between them you actually have, actually, yeah, I think I should even remove these, because as we'll see that we'll actually assign some potential symbols for these. But anyway, so between these two pins you actually have a resistor. All right, this is, you actually have an input resistor. And wait, I myself said I'll be using the box, the rectangle as for the resistor more often. So yeah, I'll stick to my words. Although, like for my university, it seems like the zigzag is more popular, so I kind of got in the habit of using that. Okay, so that's your input resistor, and you have your output terminal here. Okay, coming out from here. Okay, um, this is directly connected to, whoops, again, by habit. I'm really sorry for wasting so much of your time. I know, bit is fine, but I cannot waste too much time uh, of my viewers, obviously. So wait, I should draw that a bit bigger. Should draw that a bit bigger. So this is this even going to fit? um, Sorry. Okay, so I'll actually draw it right here. So here what you have is, I think you can recognize this well. This is going to be a dependent source. Okay, it's actually a dependent voltage source. It's going to be dependent voltage source, and this is connected to the ground. This is connected to the ground. Correct. Actually, I'll draw the ground in green uh, just to be clear. This is not a cell. That's not a cell. All right. So this is basically my equivalent circuit at the input and output terminals, which is what we care about, and we will assign some symbols. So our inverting input, this is gonna have a potential of V1. Okay, this is we say that this has a potential of V1 generally. Um, the non-inverting one will say that this has a potential of V2. All right. Your input resistance, okay, that's going to have a resistance, a value of, let's see, R sub I, okay, R sub I, um, okay, and well, I'll just mention that a bit later. Okay, so that's done. Your output resistance is going to have a value of R sub O, R sub O. Your output, the output voltage itself is V sub O. This is V sub O. Okay, and your well, your your voltage, your dependent voltage source. This is going to be your VCVS. This is obviously this depends on some sort of voltage difference, and that is what we're going to discuss now. So the voltage difference that it depends on is actually the one between V2 and V1. Okay, it's actually, so if um, this is VD. Okay, like this VD. Okay, it's called the differential, let's see, what is it called. It's called the differential input voltage. Okay, um, quite a long name. So VD, V sub D, is actually equal to, as we can see, so this is, and the plus is at V2 and the minus is V2 at V1. This is basically the difference between V2 and V1. Basically the difference between the V2 and V1. And now this is exactly what I was waiting for. This is the reason why your inputs are named as so. V2, remember, this was your, oops, sorry, V2 was the signal or the voltage at your non-inverting input, right? This was the non-inverting, right? This was the non-inverting input, and it is because this is which in this VD. Okay, this is actually plus. Okay, this is, we keep it as it is. Okay, just as it is. But the inverting input, what do we do with that? Well, we take the inverting input, and we actually flip it. I mean, we actually change its sign, right? We actually reverse its sign, right? So we make it negative and then we add it. Okay, basically we're subtracting, but you could think about, we are, think of it as we are making it negative. Okay, reversing its sign, or inverting it. Okay, basically you're inverting it. So this is inverting it, inverting it. And obviously v2, since we just kept it as it is, we didn't invert it, so that's why it's non-inverting. So we inverted v1, okay, by the minus sign here, and then we added it, okay, to the non-inverted v2, and that's why you get vd, v sub d, and that's why that input terminals are named as such. Anyways, then you have your input resistance. I'm going to talk more about that a bit later, but well, I'll say it for now. It's actually a very big resistance. Then you have, well, this on the input side, the equivalent circuit on the input side. There's going to be a lot of stuff in the middle. Okay, as I said before, it's very complicated, um, a very complicated circuit element with a lot of stuff inside. So we're not going to care about all those. Just jump right into the output. So at the output end, well, this is your output voltage. Obviously, you have your this is, and inside it's directly connected to you an output resistance. Okay, R sub O, and I already mentioned that this is actually a pretty small resistance. But anyways, we'll talk more about that later. And well, this is you have VCVS, right? Your it's a voltage dependent voltage source. Okay, voltage control voltage source. Well, big question right here, the elephant in the room is, what does it depend on? Okay, what does it depend on? What's the formula for it? So this is actually dependent on my V sub D. Okay, my V sub D. This is the value, the voltage of this. The value of this is actually A into V sub D. And well, what is A? It does have a name. It's called the, see, A, your factor by which you're multiplying your voltage difference. Okay, this is called the let's see, let's get this right. I don't want to make a mistake here. Open loop voltage gain. Okay, open loop voltage gain. Open loop voltage gain. And why is it named so? Well, I'll explain more. Hopefully I'll explain more when we talk about feedback and all. But for now, just keep this in mind. This should serve as a simple explanation. At the very least, the way we drew this circuit, as it is, okay, obviously there's wait a second. Yeah, okay, the way we drew the circuit as it is, obviously, if you just think about it, or even apply KCL, there's no other wires or connections here, right? So the current here is zero, right? Okay, either way. Okay, so there's no potential difference across R sub 0. So what you'll get is your V sub 0 here. Okay, here your V sub 0 is actually equal to the value or the potential difference of this this VCVS. Okay, your voltage dependent voltage source. So this is your output voltage is going to be equal to A into VD. Okay, or your voltage dependent voltage sources value, or okay. So that should at least convince you somewhat as to why this is the open loop voltage gain, because as you can see, there's the loop is open. Okay, here the loop, there's no complete circuit here, the loop is open, and we'll discuss more about that when we learn about feedback and all. But anyways, keeping that aside for now, let's see if I missed anything again. Did I? That's why. Okay, so no, doesn't seem like I missed anything. This is going to this is becoming a really long video. I would I actually did think about before starting this is going to be a long video, but there's a reason why I don't want to split this. It would really lose its comprehensiveness if I do split this one. So I'm really not gonna. I hope you can understand why I'm doing so. I think it's better to. And by the way, the op amp that we're discussing so far, it's the non-ideal one, or the one that we're just using in practice, in real life. Um, for calculations, as you'll see later, we mostly do it with the ideal op amp. That's why I wanted to get the uh, non-ideal op amp done in a single video. Well, actually two videos. The next one is going to have just a small practice math with the non-ideal op amp, but I wanted to get it done as soon as possible because the main thing we're gonna study is actually the non-ideal op amp. Anyways, enough about that. Just a bit left, just a bit left. So we see that we see that our if we have an open loop uh, at the voltage end, okay, sorry, at the output end, our v sub 0 or our output voltage is going to be our gain multiplied by our voltage difference between the two input terminals. This is one thing to note, that our gain is actually pretty big. Okay, our gain is actually pretty big. I'll mention the normal the typical ranges for them later. That's going to go into the explanation for the non-ideal, sorry, the ideal op amp. But anyways, so what I wanted to tell, what I wanted to discuss is, so this is a pretty large, gain, a pretty large number. So, and this is multiplied with some other number. So you might think, so okay, so your v sub 0 can actually be really large, right? Your v sub 0 can actually be pretty large, and this is a linear equation. So it's pretty natural to think that it can go, as it can become as high as you want, close to infinity, or very large. But actually that's not true. That's actually not true. And this is again because of the things that are done inside. Okay, so we won't go into the mechanism exactly, but uh, what we see is, let's see, I'll try to draw some axes. Okay, so if this is your, if this is your v sub 0, if this is your v sub 0, and this is your let's see, vd, v sub d, let's say. All right, so um, up to a certain portion, so you have your origin. Okay, so you have your origin 0 comma 0 here. um, it is true that up to a certain portion, around the origin, in the neighborhood of the origin, this is in fact linear. Okay, this is in fact linear as expected. Well, it's actually, yeah, so this is in fact your positive sloping straight line, as expected. Okay, but it doesn't go on forever. Okay, it doesn't go on forever. It actually flattens out on both sides. It actually flattens out on both the positive and negative, negative and negative sides, after this linear region. So here it flattens out, becomes constant. Here it becomes constant, just a horizontal line. Wait, it wasn't exactly horizontal. I'll try to do that again. Um, Here, okay. So this is how the graph actually looks like. Okay, um, as opposed to how we might think from this equation. Well, it is true that in the middle right here, it does follow this equation. Okay, so this linear region, this is actually called the linear region, quite simply. So this is the linear region. This is the linear region. Okay, um, so, and for this one, you have your v sub 0 is equal to a into vd. All right, and these two, and the other two ends where the voltage, your output voltage basically becomes constant. Okay, or more fancy term for that is becomes saturated. Okay, these here, the values here are actually um, limited, or at the same as your power supply. Okay, very interestingly, so this is one other place, and might even be the last time, or close to the last time we're gonna mention the power supply for the rest of the series. But anyways, um, the maximum and the minimum voltages here, um, output voltages here, are actually limited or determined by your power supply. So if you remember this, and we'll just gonna look back on it, the positive power supply and negative power supply. So this was plus VCC, this was minus VCC. So In other words, your magnitude, if you just want to take the magnitude of the size, it's VCC, right? And that is what actually limits the the maximum positive and negative values here. This is the positive saturation value here. Okay, so this part right here. Um, the fancy name for this is the positive saturation. This is the positive saturation. Basically, your voltage is not going to increase anymore. No matter how much you increase VD, your output voltage is going to remain constant. Okay, at VCC, or you could say plus VCC. Okay, and below below you actually have your negative saturation. um, think the naming is obvious here. So that was positive, so this was negative. So negative saturation. So this is your negative. I'll just write sat. So negative saturation, and the value here is negative VCC. All right. So this is how our non-ideal op amp or practical op amp actually operates. So you have a linear region in the middle. Okay, but if you increase and it if you stay in a certain range, okay, of VD, and I think you can see the range is actually going to be pretty small, because um, okay, so like the VCC is actually not that large. It's going to be from 5 to 24 volts. A is very large, and so the range for this linear region is actually pretty small. It's actually pretty narrow. All right, and if you go beyond that, you just get your a constant value on either end, so it becomes saturated. All right, so and well, uh, one last thing to mention is we actually want our op amp to operate in this linear region. Okay, the op amp is intended to operate here. Okay, so this is intended, the op amp we intend that it operates here. Okay, so this is the intended operation region. Okay, or it should operate here. Okay, it should operate here, right? We don't want to go into the saturation areas. So anyways, I think that's about enough mentioning, not mentioning, enough investigating the non-ideal op amp or a practical op amp. I think we have learned enough. So basically, we saw what an op amp is, learned a bit about that, saw what the pins do, drew a diagram of the whole, circuit diagram of the whole op amp. Simplified it, we said, there are only three pins, the terminals that are actually important, saw their roles, saw what's connected here and there, the equivalent circuit at the input and output ends, and finally we saw, the relation, or the working or operation graph. There's really no formal name for it, at least I don't think so. But anyway, so for the output voltage based on the differential input voltage. All right, that should be it. In the next video, we're gonna practice problem with this non-ideal op amp. Before we only talk about the ideal op amps, and possibly don't talk about the non-ideal one ever again. But anyways, I'll talk about all that later. So yeah, see you later and study smart.